In this segment, we're going to review some of the conventions and terminology used in NMR. We'll focus primarily on carbon NMR, and you'll be able to rationalize why certain signals appear where they do in the spectrum. Let's start by looking at this figure that's in the notes. Here we're looking at the layout of a typical NMR spectrum, left to right. You have the downfield is referred to all of the things that appear as you move to the left on this figure. Upfield is referred to the direction that's on the right-hand side. So nuclei that are upfield are there because in the old days you'd have to turn the magnet strength up in order to see those resonances. So those are highly shielded atoms, things like tetramethylsilane, which we see marked here as the reference point with zero chemical shift. So on the upfield side, here's where maximum shielding would be occurring. The electrons are shielding the nuclei from the magnet. On the other end of the spectrum, downfield, we find atoms that are de-shielded. In other words, the electrons are not protecting the nucleus from the magnetic field, but in fact they are adding to it. Their motion, electrons in motion, create magnetic fields. So in these cases, the magnetic field is actually greater in the vicinity of the nucleus because of the electrons. Paramagnetism explains this, the movement of electrons to generate magnetic fields. Paramagnetism explains that. So the atoms that are upfield, the paramagnetic contribution is very small or zero, and the atoms that are downfield, the paramagnetic term is the greatest. Finally, you could talk about the current density, and that means the electron probability of the electrons that are moving. They could either be moving in opposition to the field, that's what you have in the upfield case, or they could be moving so that they're aligned with the magnetic field. That's what you have in the downfield case. So with that explanation, I have now several cases to put on this spectrum. I've already put TMS, the reference point, here, but there are going to be 4 items that are more shielded than TMS and 4 items that are less shielded or downfield from TMS. So 8 things altogether to put on this diagram. Here are the 8 things: methane, C4+, C4-, C6+, C2+, methylcation, benzene, and acetylene. Can you locate these items on the spectrum? Give it a try and give a brief explanation as to why you picked that. So take, for example, of this list, first identify which of these 4 would be more shielded than TMS, and then see if you can put them in the right order, and which 4 would be less shielded. So pause the video at this point, come back and check your answers to see if you've laid them out properly on this chart. Okay, we're ready to look at the answers then. Here's what we would find if we were to measure these things. Although the numbers that I'm reporting here are actually Gaussian numbers, the theory is listed here. If we were to run TMS with this level of theory, we would get 182 parts per million for the shielding. So I'm going to set 182 equal to 0 on this scale, so that there are some negative numbers that are upfield from TMS. That means that they would have a greater than 182 shielding. And there'll be some numbers that are listed downfield from TMS. That means that they would have a lower than 182 parts per million value listed in the table. Let's start over here at the upfield case. Did you correctly identify methane, C4+, C2+, and C4- as being more upfield than TMS? I hope you did. The reasoning there would be that these have electrons that are in completely filled shells or subshells, right? C4- has a completely filled 1s and 2s and 2p subshells, so that's going to be highly shielded. We put that at the very far end, upfield from TMS. Carbon double plus would have a completely filled subshell. The 2s2 subshell there would be filled, and for C4+, you have a 1s subshell that's shielding the nucleus. Methane and TMS are very close. Methane is a little bit more shielded than TMS, and so it would be found here at minus 12 parts per million with respect to TMS. How about in the other direction? You have 4 of the compounds here, or I guess this atom, C6+. You find, let's look at the extreme, try to explain that. Methyl cation is at the far extreme, well downfield from TMS. And the explanation for that is that if you look at methyl cation, here we see it at the left, carbocation CH3+. What is that? The hybridization at that carbon is an sp2 hybridized orbital, making bonds to the hydrogens. But then there would be one unhybridized p orbital that wouldn't have any electrons in it. Compare that to a carbanion and a methyl radical, right? They have a different electron configuration. The carbanion is sp3, and it's got electrons in this lone pair. A methyl radical is sp2, but it has one electron in the unhybridized. So for methyl cation, we have the ability for the electrons, when they're stirred up by the magnet, they can go from these bonding locations into this unoccupied p orbital. So that means when we put this carbocation in a magnetic field, this methyl cation in a magnetic field, the electrons, rather than opposing that magnetic field, they will actually allow the magnet to stir them up and go from the bonds into this unoccupied orbital. So it'll actually increase the magnetic field at the nucleus. That's why we see this as one of the most de-shielded cases. It's one where the paramagnetic term is the greatest. The electrons act to add to the magnetic field, and it's found well downfield at 397 parts per million with respect to TMS. So its actual shielding would be, you'd add that, it'd be in the 580 parts per million range. Benzene is halfway between TMS and methyl cation because it also is an sp2 hybridized orbital, but it has one electron already in that space, and so the paramagnetism is not as great. Acetylene, let's look at a picture of acetylene here for a moment. Acetylene has sp hybridized orbitals at each carbon. It'll have 2 sets of unhybridized p's that form the pi bonds. And so these electrons form kind of a ring around the axis of acetylene. So they do resist somewhat the magnetic field. They shield the nucleus because of this, all of these electrons that are in this ring around the axis. But they also would allow some current density to go along with the magnetic field. And so that's why acetylene appears fairly well shielded, but not as shielded as a normal sp3 type situation like we see in methane or TMS. The last one on here I haven't talked about yet is the C6+. What's carbon C6+? That's a carbon with all of its electrons removed. It's a naked carbon nucleus, if you will. And its shielding is going to be 0. And so with respect to TMS, that would locate it at 182 parts per million. There's no shielding at all. This is where the sigma term would be 0. And it's found somewhat in the middle of the carbon spectrum. So there's no shielding going on, but there's also no paramagnetism going on. So you could also think of this as sort of the balance point in the spectrum. Everything to the right of C6+ would be shielded to some degree. Everything to the left of it would be deshielded. I've filled out the table here with these explanations. You can take a look, pause the video, or add to your notes here at this point anything that you missed from my verbal explanation. So now I'd like to give a little more background to this paramagnetism rather than just sort of argument based on a orbital picture. We can actually calculate this paramagnetism or try to understand these shifts by analyzing the details of a Gaussian calculation. So let's take our methyl cation example here, where I tried to explain this very deshielded paramagnetic term greatest case, and look at how the details of the calculation can confirm these arguments that I've presented so far. So here's a WebMOS summary of methyl cation. You notice it's a flat structure, planar structure, carbon with 3 hydrogens and a +1 charge. If we look at how this molecule is laid out, we'll need to look at the raw output to see where the XYZ coordinates lie, because what we're going to do is we're going to analyze this chemical shift in terms of the different directions that the magnetic field being applied can affect changes in the electronic structure. So clicking on raw output brings up the file, which I can blow up here. And if you recall from the earlier video, if you want to quickly go to the section dealing with NMR, you can search for ppm. Those are the units used in NMR, parts per million, and it's the only place you'll find ppm in the entire log file. So I just searched for ppm, and that quickly brings me to the section of output where the NMR is displayed. You see the atoms listed here one by one: carbon, hydrogen, the other hydrogen, and then the final hydrogen. So there's sections here for each. In each section we have labeled the isotropic shielding. This is the absolute shielding that is averaged over all directions. That's what isotropic means. Look at the value for the averaged over all directions absolute shielding for the carbon in methyl cation. It's negative. It's actually minus, right? This in TMS, this number would be positive 180, but in methyl cation, it's minus 221. So that kind of indicates to you how the atom, this particular atom, has a very high paramagnetism term in the chemical shift. It's very much de-shielded, not shielded. Those electrons are not protecting the nucleus. Those electrons are adding, their motion is adding to the magnetic field. So if you see a large negative shielding, that's what you're seeing in that case. Now there's also a bunch of numbers underneath here that are labeled with Cartesian axes. And so what we see here is a breakdown. This is called a tensor matrix. There's 9 numbers here. What does this mean? XX. XX means this is the shielding that is due to the magnetic field applied in the X direction, and it's how it affects the electrons in the X direction. Whereas the YY is a magnetic field applied in the Y direction. This is the shielding due to the electrons moving in the Y direction, etc. If we focus primarily on the diagonal elements, those are the strongest contributors to the isotropic shift. The off-diagonal elements add only to the anisotropy. To interpret this, let's focus just on the diagonal elements for the moment. We see in the X direction, huge negative number. In the Y direction, huge negative number. And in the Z direction, a positive number. So this is telling us that in the X and Y direction, the magnetic field is going along with how the electrons are moving. But in the Z direction, the electrons are actually opposing the magnetic field. So even in methyl cation, where we said that this is a highly de-shielded case, there is at least one direction where the electrons are shielding. Now, to explain these directions, X, Y, and Z, you have to understand how the molecule is laid out. And so if we go back to the coordinates, here are the coordinates of this molecule. The carbon is at the origin, 0, 0, 0, and then one of the hydrogens is along the y-axis, and the z-axis is the out-of-plane direction. So that means that as we see the figure here, the z axis is basically the grade unhybridized p orbital. That's the axis that is along. And the x and y plane is where the molecule resides. Okay, so now let's go back and think about a magnetic field applied in these different directions. So if a magnetic field is applied along the z-axis, that means it's going to be stirring up electrons around that axis. And so that would be moving electrons from one bond into another in this case. So that would, the molecule would want to resist that, because electrons would be going into places where electrons are already residing, right? So that's why that term is positive. The z direction is positive. But if in the x and y directions, think about that. If you've got the x-axis, which is horizontal here, a magnetic field in the x direction will stir up electrons around that axis. That's going to move electrons from these bonds into this empty space. Electrons are going to allow that. They're going to go along with that, adding to the magnetic field. Coming back now to the picture that we had of the output file. Hopefully you can see why, it makes sense at least, why the x direction and the y direction, the in-plane directions, are hugely negative and are the strongest contributors to the shift. And then the z direction has a slight resistance or positive quantity. It all averages out to be about minus 221, which puts it well downfield in the NMR. So I hope this overview of terminology gives you an idea of why things appear where they do, and also that you can dig into the Gaussian output file and find out more details about not only the shift, but how the different directions of the magnetic field affect that shift.